So here is a question on work energy and power that we want to try together. Okay, it's saying a force of 62.5 Newton is applied on a trolley of mass mkg parallel to the inclined surface. It is shown to keep it moving down an inclined surface at a constant velocity. The vertical height of the inclined surface is 12 meters. Refer to the diagram below. Okay, so a kinetic frictional force of 35.5 Newton acts on the trolley as it moves down the inclined surface. So there is our diagram, right? So of course there are questions, but before we attempt the questions, there's something that I wanted us also to take note of. Whenever sometimes the examiner gives us the information, like the information just above the question, there are certain key terms that the examiner would make effort to highlight as a hint or a clue on how to answer the questions that follow. Like, for example, we realize that constant velocity here has been highlighted in uppercase. There is a reason for that, so that you can pay attention to that detail, which I also want you to do as you are attempting certain questions, to pay particular attention to the clues and the information that the examiner has made effort also to highlight on the information above. Okay, so let's try to answer the questions then together. The first question is saying, write down the name of the conservative force that is acting on the trolley. Let's first define what a conservative force is. So a conservative force is a force which, when it does work, the work is independent of the path taken by the object. So a very good example of a conservative force is weight or gravitational force. So gravitational force is a conservative force. So apart from that, we also have magnetic force and electricity force. But on this diagram, the conservative force that is acting is actually weight, the gravitational force. So we've answered that part. Let's go to 5.2. 5.2 is now saying calculate the work done by the kinetic frictional force. So work done by the kinetic frictional force is given by kinetic frictional force Fk multiplied by delta x multiplied by cos what? Cos theta. That's the information. Okay, so kinetic frictional force we've been given. We are told that kinetic frictional force is 35.5 Newton. As a matter of fact, it's also very important to realize or to remember that, of course, kinetic frictional force always acts opposing the motion of the object. So obviously the kinetic frictional force is not acting in the same direction as the displacement. Remember, this theta here is the angle between the force and the displacement, because work by definition is simply the product of force and displacement, with the force and the displacement acting in a straight line. So we are saying that this theta here can either be 0 degrees or can be 180 degrees. 0 when the force and the displacement are acting in the same direction. 180 when the force and the displacement are acting in opposite direction. So let us first identify delta x in our case, the displacement from A to B. Do we have it? No, we have not been given, but can we not find it? We can with the information that we have. This marks our opposite to the angle given. This marks our hypotenuse. So which ratio can we actually use? We can use the sine theta ratio. So sine theta is equals to opposite over hypotenuse. So we can substitute what we have. Sine 30 is equal to opposite our h, the perpendicular height, which is 12, over our hypotenuse that marks our delta x. So making delta x the subject, it means delta x is equals to 12 over sine what? Over sine 30. So there we go, right? So in calculating, what do we end up having? 12 divided by sine 30, we end up having what? 24 meters. So of course, we punch that on the calculator, we get delta x here is 24 meters. That marks our delta x. So we come and perform the calculation, therefore, for work done by the kinetic frictional force. So the work done by the kinetic frictional force is going to be given by 35.5 multiply by 24, multiply by cos. Remember, theta, in this case, it can be 0 because kinetic frictional force and the displacement are not acting in the same direction. Displacement is acting from A to B. That's our displacement, is from A to B. But then kinetic frictional force is acting in the opposite direction. So for that reason, it's going to be 180 degrees. Okay, so when we multiply 35.5 times 24, multiply by cos 180 degrees, of course, the calculator will give us a value, a negative 852 joules. That marks our the work done by the kinetic frictional force. We've answered 5.2. Let's go to 5.3. 5.3 is saying write down the change in kinetic energy when the trolley reaches the bottom of the inclined plane here, inclined surface here at B. That's where we are being asked to calculate. Okay, so change in kinetic energy, delta EK, is given by EKF minus EKI, the initial kinetic energy. Okay, but EKF is going to be given by half mvf squared minus half mvi squared. Remember, kinetic energy is always given by half mv squared. Okay, so of course, now take note of what has happened now. The constant velocity means that at A, the velocity was constant as the same velocity that we were having at B. So it means that whatever the value the velocity is going to give us, it's obviously going to tell us that the change, either in the velocity or in the kinetic energy, it is going to be 0. So I'm simply trying to say that here, the understanding of knowing that at constant velocity, the kinetic energy is, the change in kinetic energy becomes 0, is what the question is asking us. So we simply have to know that the kinetic energy is obviously 0 joules. No need to perform calculations on that, but it's also kind of important to use the question to also know that the change in kinetic energy is given by EKF minus EKI. Okay, let's go to 5.4. So the question is saying use the work energy theorem to calculate the mass m of the trolley. So the question is very specific. It wants us to use the work energy theorem. So if you use any other theorem or any other energy principle, you are not actually going to get your marks because it wants you to use the work energy theorem specifically. Okay, so if that is the case, then how do we calculate using the work energy theorem? What does the work energy theorem say in the first place? That's the first thing to take note of. The work energy theorem says that the net work done on an object is equivalent to the object's change in kinetic energy, E delta EK. Okay, so the total work done on an object is equivalent to the object's change in kinetic energy. That's what the work energy theorem says. So in using it or in performing calculations using it as well, it means that the individual work done by all the individual forces that are acting is what is giving us W net. So let's try to identify that first. W net, therefore, is going to be given by what? Right? My advice is when you find it a little bit difficult to identify the individual forces that have done work on an object, try to bring out a free body diagram or a force diagram. Usually a free body diagram is also good to use, but nonetheless, just bring out a free body or a force diagram to identify all the forces that are acting. So let's try to do that. Okay, there we are on an incline. There is our object. So we are saying we have the kinetic frictional force, Fk. It's acting up the incline. Apparently, there is also an applied force. So the applied force, we have been told that it is being applied exactly in the manner that it is indicated there. It is applied as shown on the diagram, which means it's acting up the incline as well. So on our free body diagram, obviously we can portray it or we can bring it out in that way as well. So there is our applied force of what? 62.5 Newton. Then we happen also to have the gravitational force acting downwards. There is our gravitational force acting downwards. And then there is our normal force acting upwards. There is our normal force acting upwards. These are the forces. Now, from our understanding, the normal force shall obviously do a work of 0 joules because the angle between the force and the displacement, mind you, the displacement is down the incline. So the angle between them is going to be 90 degrees. Same applies with the perpendicular gravitational force. It's going to do a work of 0 joules as well. So which are the forces that we are going to consider? Number one, work done by the applied force plus the work done by the kinetic frictional force plus the work done by the parallel gravitational force. Remember, on an incline, the gravitational force has to be resolved into its horizontal and into its vertical component. So we have the work done by the parallel gravitational force plus, of course, the work done by the normal force and the work done by the perpendicular gravitational force. But however, these two here are going to do work of 0 joules, 0 joules, 0 joules. Why? Because the angle between the force and the displacement shall obviously be 90 degrees. It's very good to quickly note that and save our time. Okay, so already as well, we have indicated, we have already seen on 5.3. There is another thing again that I wanted you to take note of whenever you are looking at questions. What usually happens is from 5. Let's say, for example, from right now we have 5.1, 5.2, 5.3, and 5.4. Usually what the examiner does, or what examiners do when questions are being set, the information you are gathering on the first part of the questions, where you are answering the questions on top, you might as well need it as you go down, because it serves also as hints on how to answer the questions that follow. Like right now, we have just come to notice that the change in kinetic energy obviously is 0 joules. That information becomes also necessary to recall on 5.4. We should also consider that. Okay, so let us now perform the calculation. Okay, so with the kinetic frictional force, we have already calculated. So we need the work done by the applied force plus the work done by the kinetic frictional force plus the work done by the parallel gravitational force plus 0 should be equal, which 0, the work done by the normal force, and the work done by the perpendicular gravitational force is equal to 0, the change in kinetic energy. So we can substitute now force applied FA multiplied by delta x times cos theta plus, of course, FK times delta x cos theta. I think this one we've already calculated. We got negative 800 and what? And 852 joules plus work done by the parallel gravitational force is going to be given by FG parallel multiplied by delta x multiplied by cos what? By cos theta is actually equal to 0, right? So substituting on the work done by the the work done by the applied force, we have an applied force of 62.5 multiplied by 24. Mind you, we got our delta x is 24 meters. So multiplied by 24 times cos. So you see, many candidates actually have a problem in identifying the theta. You just have to know, the easiest way of knowing is when the force and the displacement. How do you know the direction of the displacement? The direction of the object is actually the direction of the displacement. The object is going down the incline. Apparently, that's also the direction of the displacement, which means the applied force in this scenario is not acting down the incline. So I want you to desist from the common thinking of just saying an applied force is acting down the, it's always, its angle is always going to be 0 when you are calculating the work done by the applied force. No, it's not the case. Like in this case here, the applied force is actually acting in the opposite direction as to the direction of the displacement. Therefore, we are going to place here 180 minus 852, right? Plus work the parallel gravitational force. Parallel gravitational force, by definition, it's going to be given by Fg multiplied by sine theta, right? This is the formula. So what we simply do, we are substituting Fg is given by mg, mass times the gravitational acceleration. So what is the mass of this object? That's m. We don't know it because the question is asking us to calculate m here. Multiply by 9,8, multiply, so this is mg, multiply by what? Delta x. Delta x, mind you, is 24. Multiply by cos what? Cos 0 is therefore equal to, is therefore equivalent to, it's equal to 0. Remember, so if this is cos 0, is equal to 0. The change in kinetic energy. Okay, so we first simplify the first part. So in simplifying, 3262,5 is 3262,5 times 24 times a cos 180. That's obviously going to give us a negative 1,500. It goes to the other one, negative 852. That marks the other one, right? 852. Okay. All right, 852. Right. Plus, let's go to m. 9,8 times 24 times cos 0. That's 9,8 multiplied by 24 times cos 0. Obviously, it's going to give us 235,2 m is equal to 0. There we go. So we can first simplify this first part. Negative 1,500 minus 852. Transpose it to the other side. Obviously, it's going to give us, we have 235.2 m is equal to, this is giving us negative 2,352. Transpose it to the other side, it becomes positive 2,352. Okay, so divide now by that value, divide by 235.2, divide by 235.2. So m is going to be equal to, we get a value, of course, 235.2 divide into 2,352, obviously we get 10. So that marks our m, meaning to say m is 10 kgs. We have arrived at the value of m. So that's basically what you are doing. Of course, here we've been confined to the work done, to the work energy theorem. But mind you, usually the question can say, use the energy principles. You can either use the work done, of course, the work energy theorem, or the work done by non-conservative forces. But however, you can't use the principle of conservation of mechanical energy here because we are saying energy has not been conserved. So that's basically what you do. Okay.